For number 4, how do you think the distance that light passes through the sample affects the observed optical activity? So your observed activity is directly proportional to the distance that the light passes through the sample. You're able to take those measurements, and like we said, the measurements go up as the concentration goes up. It's directly proportional. That makes sense? Yeah. Yes? So you have about 5 more minutes. Be sure you have written up what you need. Written up.
You're right. You say it too fast. I didn't write it.
Okay, well, which one do you need help with?
I need help with 2, 3, and 4.
2, 3, and 4 on, and what do you need? Okay, so number 2, was it reasonable to use your graph? It should have been, yeah, 3 and 4. Very reasonable, because if your graph, if you went 0, 1, 2, 3, 4, and you, this one came in at 7.5 or 8, which is what I would have expected, then, yeah, it would be a nice line graph, right? Straight up. So it should work. There you go. And then dividing, let's see, if the optical activity is way different.
Check your forums tomorrow.
For number 3. Between 2 known values. Yes, in that case, if it wasn't between 2 known values. We didn't do it between 2 known values. That was if we had put it at 35. We wouldn't have taken it here, but we didn't put it at 35, because it's higher. So if it was between 2 known values, then yeah, it was real easy to predict. All right, we're gonna go further. So you can still predict the graph. If it's done and you're happy with your answers and you know they're thorough and good, then you're not going to take it home and revise it. You get it how you want. Okay? Yeah.
Solutions identified. Because we're math geniuses. Geniuses are geniuses. I would think there's one. What's that? Darcy one.
One part of the way.
Darcy.
So,
Mom.
Second, place it right in the first.
All right, so I didn't have time. Oh, I don't finish that. I'm gonna get back on this.
One block with the one direct. And the other block is indirect.
We can go back.
Because it wasn't running.
I think it was fine. Like, me and yeah, but I don't think I'll that's why we watched the first guy movie with the dirt. They want to get it. We don't. I forgot that there's if Bailey gets things done on Monday, then it's like he posted it by Monday, so I might update my answer. But if he doesn't, we can probably find. You're not sure that I don't. I got smart. What did he make? E equals MC Hammer. All right, I'm gonna go check the car. You guys
I'm running around. He wants mine.
That was Monday. I was gonna text you. Please send me a text.
Take a seat.
Oh, no. It's been I think there's. No, a few minutes ago it was legit like that. It's really like that. Did you just say baby's chat? I'm not.
Yes, I think I told
Oh, baby. I need someone to mess this up. I cleaned it first. Yeah, no, Dave. Don't.
I'll give you $5.
I do need a ride home. And you are in a different direction.
I'll give you $10.
No, it's not.
I'll give you $15.
Do you have $15 on you? Oh my god. Bro. Yeah. I'm going to do stuff. I won't move. I don't trust that.
All right, gang, let's get going.
I can't drive yet. It's you get enough for you can ride home plus a little extra, you'll probably step back.
What?
You have no space, please. Someone is in an accident and they're bad.
I'm sure someone's.
You don't go one. They won't let me.
There you go.
Move to them. There you go. Sit on it. I would. Then do it.
I would.
Who cares about
I
pain?
have reasons for not.
What?
You don't need photos. Can you
Yeah.
I'm good.
Yes, I do.
Oh, my God, I thought you were like.
Thirsty.
No.
Need to be comfortable.
Oh, never mind.
Yeah, around.
Why
No.
All right, gang, you about ready?
It's actually who.
Stop it. I don't know how to down, so.
Lane.
I love it. You just moved to, like, sorry. It's not fun. I've been here for years.
Yeah.
So, why should I take Stephanie like actually fine?
I didn't even do it.
Yeah.
If you don't have shoes on, no, I see Bigfoot and it doesn't good.
It doesn't look that.
No, it's my God. I have a suspicion why it's okay, maybe that's fine.
By my shoe.
Okay, gang, there is a mentee leader today, just so you know, before we get to it.
Here's another lunchbox.
Where do I sit?
Make sure to put one.
Oh.
So heads up, are we listening? Okay, heads up, we've had a couple technical problems this morning with the computer talking to the TV because we've had to change out some of our normal stuff. So hopefully we will not lose it. There might be a lag. I apologize for the lag. We're dealing with it. Alrighty, so do I have everybody? Okay, electromagnetic spectrum we're doing today. First off, everybody, I think everybody, there are a couple of you I don't think that I have a comment on the video for. Be sure you comment on the video from last week.
I did.
Yeah. It wouldn't let you?
There's not a comment option.
There should be. It's probably your settings. It's probably whatever settings are on your side. But you did watch? Okay, so I'll try and remember to go back and change that because I already checked yours. I didn't see your comment. So be sure that you watch the whole thing. I was really bummed that I missed that lesson because I really like sharing that music part with you guys. It's fun. It's really fun. And you got to see.
The vocal cords look kind of like frogs.
Yeah, they're weird, right?
Videos were
They're real weird. Do what?
unavailable for that.
Okay, somebody else said that too. So that's your settings on your side. That's some setting you've got on your YouTube that you're using. Because they're regularly publicly available videos. So all right, so let's move into our discussion today, electromagnetic waves. It's a shorter lesson, so I have a really fun Mentimeter at the end that should be entertaining. So we have all the rainbow rats today. I gotta love the rainbow rats are super sweet. So electromagnetic waves, these are transverse waves consisting of changing electric fields and changing magnetic fields. Now, last week our lab was going to be about sound. Did anybody look at the lab? I excused it.
Yeah.
It had to do with how fast sound travels. What kind of a wave is a sound wave? It's a longitudinal wave, right? Okay, so whereas electromagnetic waves are transverse waves. So these are waves like light waves, right? All right. More than just light, though. There's the visible light and everything else. All right, so what do we call it when something is exerting an electric force on charged particles? All right, Liam.
Electric field.
That's an electric field. And then what do we call it when you have a magnetic force, Caitlin?
Magnetic.
A magnetic field. All right, so you have electric field and a magnetic field. So electromagnetic waves are produced when an electric charge vibrates or accelerates. Okay.
Oh, the little.
I like his little bow tie. It's very cute. All right, so how do they travel? So electromagnetic waves can travel through a vacuum or empty space as well as through matter. Now you were seeing today visible spectrum electromagnetic waves that were moving through matter with different densities, right? We were increasing the densities with our sucrose solution. So that should have been changing how they were moving. So what's the transfer of energy by electromagnetic waves traveling through mass across space? PJ.
Electromagnetic radiation.
There you go. Electromagnetic radiation. You have a brownie point?
In the binder, it says the electromagnetic waves can travel through a vacuum or empty space. It doesn't.
Oh, all right. Here, one more. Yeah, there we go. All right, cool. There's one more for you then. All right, so we're gonna watch this guy. If this acts weird, I'm gonna switch it over to direct YouTube because it's been a little weird this morning. But we're gonna talk about Michelson's experiment. So this dude installed a mirror that didn't move, and then he also installed an octagonal mirror that did move. It's kind of hard to understand what that means until you visualize like a diagram of the actual mirrors moving. So this shows you how he was able to determine the speed of light, which is roughly 3.0. Okay, make sure we have volume. Oh, where's the code for that? I didn't even know where it went.
Speed of light shouldn't really be that hard. Light moves with uniform motion through a constant medium, so we can use the formula V equals d over t. The tricky part is trying to measure t. Because even if you pick a distance that's really huge, like the distance around the entire Earth, the time it takes light to travel that distance is only about 0.13 seconds. So what we need in order for this to work is a very, very good stopwatch. The stopwatch would come from American physicist Albert Michelson, who between 1878 and 1926 refined a method that could measure the time taken for light to travel between 2 points. This is the Michelson rotating mirror experiment. A ray of light from a light source reflects off a rotating 8-sided mirror. Light travels a long distance. In this case, Michelson had it move about 35 kilometers one way through an old abandoned mine shaft between 2 mountains in California. The light hits a flat mirror at the end of the shaft, reflects and comes back through another 35 kilometers, then strikes the rotating mirror again and is sent perfectly into the observer's eye. But how can a spinning mirror be a stopwatch? The trick is that the frequency of the spinning mirror, or how long it takes to make one full revolution, can be adjusted. Starting from rest, the frequency is slowly increased as light shines on it. Light reflecting off the spinning mirror will only be observed if the ray hits the observer's eye exactly. This only happens when the spinning wheel comes into the exact same alignment it was in as when it originally was hit by the light. And because it's an 8-sided wheel, this occurs for the first time at exactly 1/8 of a revolution. The genius of the Michelson experiment is that the spinning mirror's frequency can be used like a timer. As long as we remember that it's going to take the light exactly 1/8 of a revolution of that spinning mirror to travel its 35 kilometers one way and its 35 kilometers back the other. Let's look at an example. Let's say that we get the mirror spinning at a frequency of 525 hertz, or 525 revolutions per second. And at that frequency, the observer can see the light. We can convert the frequency into a time measurement by using the formula period equals 1/frequency. The t in this formula is period, or the amount of time in seconds needed to make one full revolution of the wheel. Running this calculation, we get a period of about 0.001905 seconds. Now remember, this is the time it takes the spinning mirror to make one full revolution. But in this experiment, we're only concerned with the time it takes to make 1/8 of the revolution, as this is the amount of time needed to let the beam of light move 35 kilometers there and 35 kilometers back. So we'll take our period and multiply it by 1/8 to get a time of 2.3810 times 10 to the negative 4 seconds. This is sort of our there and back time. Finally, we can use the uniform motion formula. The total distance will be 70,000 meters, since the light moved 35 kilometers or 35,000 meters one way and 35 kilometers back the other way. And we're going to use a time of 2.3810 times 10 to the negative 4 seconds. Dividing these, we get a speed of light value to be 2.94 times 10 to the 8 meters per second, which is pretty close to the accepted value for the speed of light at 299,792,458 meters per second. Now you know how Michelson worked at the speed of light, but is that speed correct? How does he know that the speed is the same going forwards and backwards? Check out this Veritasium video. He does an amazing job talking about the one-way speed of light versus the two-way speed of light. And after you're finished, you can ask.
We're going to do that one. So when you're doing calculations at this level of physical science, we often just use the whole number there, the 3 times 10 to the 8th meters per second, instead of the 2.94, blah, 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 going on. Move on. Thank you. All right. So that's one of those ones that when I read it, I was having a hard time visualizing it. So the video actually really helps. You can see what they mean by an 8-sided mirror. It's not like a flat stop sign, right? It was more like a barrel, right? So your electromagnetic waves vary in wavelength and frequency. Electromagnetic radiation sometimes behaves like what and what? Okay, Lucas.
Waves and frequency?
Waves is one.
No.
And
Particles.
I was gonna ask Xander, but okay, yeah. All right, waves and particles. All right, so this is light. This is why light is different. It's waves and particles. So today, when in lab, when you were using the polarizing film, were you studying light as a wave or a particle, Drew?
A wave.
As a wave, right? You're studying it as a wave. So you can think of polarizing film as a fence. Think of it like a fence, like a fence with slats, like a picket fence. Okay, if you're standing on one side of the picket fence, you can see the yard on the other side through the spaces in between the slats, right? And then, but think of it as the spaces between the slats are equally sized to the slats. So if you have a 4-inch slat, 4-inch space, 4-inch slat, 4-inch space. Okay, so that's one layer of polarizing film. If you were to take another section of that fence and turn it at 90 degrees, now you've got, it's almost like a waffle weave situation, right? And that's why you're getting all of the light blocked out when you have it at exactly 90 degrees. Does that make sense? Because you've got light that goes this way, and then you've got light that goes this way. So if the light going this direction is getting blocked when the slats are going this direction, then you flip it. Now you've got the light going this way that can't get through. All right. So that's with waves. Oh, that's weird. I don't know what it's going to be weird today, y'all, until we get it worked out. So now we got this guy Young. Okay, so Young is the guy who had evidence for waves. So Young passed a beam of light through a single slit and then a double slit to observe brighter and dimmer bands projected on a dark screen. Okay, so we're going to talk about all these different scientists at the end, and we're going to kind of put them in a bit of a timeline and everything, so you kind of understand who's doing what when. Oh, it's going to get weird, guys. I don't know. Oh no.
Well, it's back.
Okay, all right. I just got to keep wiggling my mouse apparently. So yes, so that's Young. All right. So next we have the photoelectric effect. Okay, who can tell me what the photoelectric effect is? Who wants to give it a description for me? Okay, Yusuf, you want to go for it?
Well, it's like how blue light makes photons come off metal, but red light doesn't. It's because Albert Einstein proposed that. It was because blue light has a higher frequency than red light. So blue light photons have higher energy than red light photons, which is why they make
Right. So it's certain wavelengths of light. When they hit metal, they're going to produce electrons. And photoelectric, meaning they produce some light that you can see. Because your photon is your little packet of electromagnetic energy. Okay? All right. So here is your particle versus wave. And this is good visual to help you kind of get an idea of what we're talking about. So hopefully it won't disappear on us. I don't know what to do. It does that. My subwoofer kicked in well, didn't it? Okay.
You look down and see a yellow pencil lying on your desk. Your eyes and then your brain are collecting all sorts of information about the pencil, its size, color, shape, distance, and more.
No,
It,
no, no.
for the first to think more or
Oh,
less scientifically
come on.
about what light is
Back.
Okay.
and how vision works.
I don't know why it's doing that, y'all.
Including Plato and Pythagoras, thought that light originated in our eyes and that vision happened when little invisible probes were sent to gather information about faraway objects. It took over 1,000 years before the Arab scientist Al-Hasan figured out that the old Greek theory of light couldn't be right. In Al-Hasan's picture, your eyes don't send out invisible intelligence-gathering probes. They simply collect the light that falls into them. Al-Hasan's theory accounts for a fact that the Greeks couldn't easily explain: why it gets dark sometimes. The idea is that very few objects actually emit their own light. The special light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from a source, rather than producing their own. So, when you look at your pencil, the light that hits your eye actually originated at the sun and has traveled millions of miles across empty space before bouncing off the pencil and into your eye. Which is pretty cool when you think about it. But what exactly is the stuff that's emitted from the sun, and how do we see it? Is it a particle, like atoms? Or is it a wave, like ripples on the surface of a plant? Scientists in the modern era would spend a couple of 100 years figuring out the answer to this question. Isaac Newton was one of the earliest.
Band-Aid.
Newton believed that light was made up of tiny, atom-like particles, which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water. But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other.
Come on. Sorry. It's going to be weird.
Tiny solid balls, then you would expect that.
Yeah. Fun times. I love technology. I love technology. I love it.
Light that cross paths don't interact with each other at all.
What?
Light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would bounce off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond, and also when two point-like sources of light are placed near each other. Only waves make interference patterns, particles shown. And as a bonus, understanding that light acts like a wave leads naturally to an explanation of what color it is and why that pencil looks yellow. So it's settled then. Light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete patterns called quanta. But we can't just forget about properties like interference either. So these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
So if you really like physics and you really like electromagnetic spectrum stuff, you could go into quantum mechanics. Oh, yeah, that's a good one. That's lots of math. If you really like math, quantum mechanics might be for you. So, hey, some people love math.
Alex.
All right, so intensity, the rate at which a wave's energy flows through a given unit of area we call intensity. So if the intensity of light, I should say, sorry, decreases as photons travel farther from the source. So basically this is like, almost like you can think of it like how bright is the light, right? Uh-huh.
Brownie point, it says 17.2, even though it's not 17.2.
Oh.
It would be 18.2.
Oh.
It's really,
Okay, good job. You found two of them. All right, so what's the spectrum? All right, the electromagnetic spectrum. So who discovered infrared? Okay, let's see, Bailey.
Infrared, Sir William Herschel.
William Herschel. Okay, we're gonna be talking about him in a little bit. He's an interesting dude. So he discovered infrared in 1800. That's not all he discovered. All right, and the full range of frequencies, Drew?
Well, is it,
Oh.
wait, is how he found out in the slide? Kind of cool.
A little, go ahead, share what you want to share.
So basically, he had I think it was a prism. He was trying to see if different colored lights made different, like, heat, basically.
Mhm.
So he lined up a bunch of thermometers in a specific way. I think it was a prism. He had it so that it shined the different colored lights on each individual thermometer. And one on the other side had no light on it at all, but it was like right next to the one that did. And that one shot up and was hotter than all of the other thermometers. And that's because it was infrared light that he couldn't see, but it was right next to.
There you go. Yeah, that's good. So what do we call the full range of frequencies? James? The spectrum. Okay, the electromagnetic spectrum. So spectrum includes the full range. Yeah.
Brownie point. It says the electromagnetic spectrum includes all those waves, and then it has GSMMA.
Oh, it should say gamma. All right, so you found 3 today. Yeah, there's a lot in this one, I think. This one got all wonky when I transferred it. So the electromagnetic spectrum includes radio waves, infrared waves, visible light, ultraviolet rays, X-rays, and gamma rays. Okay, looking at the order of those, you can take a context clue from here. Infrared, what does infra mean? As a Greek Latin root, infra. All right, Yusuf, wrong kid, Yusuf.
Small or like?
Kinda, sorta. Jordan, did you want to give it a shot? Infra? We talked about infrasound a couple weeks ago.
Yes.
Infra would mean, you want to guess?
Low amount.
Yeah, below. Okay, so infra is below. So infrared is light with a wavelength below what we can see. Okay, so if you see infrared there, and then visible light comes after it, and radio waves come before it in this list, then what does the context clue give you there about radio waves? Think about it. Infra means below what we can see. Then you got visible light. So it's,
You can't see radio waves.
you can't see them, right? And there, it's even lower. Okay. Now you got ultraviolet, X-rays, gamma rays. What's ultra mean? Do you know? Does somebody want to give me? Caitlin, do you want to give it a shot? Oh, wait, Colin, you haven't gone yet. Yeah, it's like beyond. Okay. So we can't see anything that is at or below infrared, and we can't see anything that is at or above ultraviolet. Okay, so it gives you an idea, that order there gives you an idea of sort of how we're dealing with wavelength and frequency with those particular types of radiation. So radio waves, all right. So the type of electromagnetic waves with the longest wavelengths and the lowest frequencies are what? Okay, Yusuf.
Radio waves.
Okay, these are our radio waves. And there are different types of radio waves, and they aren't all used in your stereo. So radio waves are used in MRI machines, for example, which create images the inside of your body. What's MRI stand for, James?
Magnetic resonance.
Yes. Okay, magnetic resonance imaging. Anybody ever had an MRI? Yep. Okay, what was the experience like? It's loud. Yeah, they give you headphones? Hmm?
Like the big.
Yeah, it's like a big tube usually. Okay, so why is it loud? Do you know what you're hearing? Yeah, there's the magnets. The magnets are shifting around. So when you go in, if you ever get an MRI, when you go into the room, I laughed the last time I went and made a joke that they had to listen to dubstep all day. Because that's exactly when you go in, it's like, and it just does that, like the whole time you're in there. And then they start taking the images, and it's rattling and banging and beeping and vibrating and clattering sounds, and it's very, very, very loud. So they usually give you headphones for it. But MRIs are good because there's no real, like, it's not like X-rays and stuff. We talked about you have to limit X-rays because
Cancer.
they can cause cancer if you get too many of them. MRIs are different. So yeah, so they aren't all these radio waves are not all in your stereo. So we use them all over the place. They're everywhere. Did it go away again? Okay, hang on, maybe it'll come back. Maybe, there you go. Okay, well, we lost that first one there. Microwaves, that's our first one. I don't know why. We'll have it fixed next week. So microwaves are those with the, no, it's not. It's not loose. It's not, I'm not even touching it. I don't know why it's doing it. So microwaves are those with the shortest wavelength and the highest frequency. Okay, a second ago, we just said that radio waves had, what did it say? The longest wavelengths and the lowest frequencies. And now here we have shortest wavelength and highest frequency. So what does this tell you about waves in the electromagnetic spectrum when it comes to wavelength and frequency, Liam?
Wait, what?
Oh. Wait, what?
I'll try to answer.
Oh, okay, hold on, we'll come back to that one. If one of them has long wavelengths and short frequencies, and the other has short wavelengths and high frequency and low wavelength, or low wavelength and high frequency, what's the relationship? What do we call that? Inversely proportional. Thank you. Bingo. All right. So we're dealing with inversely proportional. So think about it. If your space, hang on, if your space between your waves is spread out like this, okay, and here's your point that you're going through. You have a long wavelength. Is that crest going to pass through your fixed point quickly or slowly? Right, less often. So that's why you have a low frequency and a long wavelength. Meanwhile, if your wavelength is much shorter and your crest is right here, how often is the crest going to pass through the point by comparison? More quickly, right? So those two things tend to be inversely proportional. Okay, Liam wanted to do the next one. Shortwave microwaves are used in what?
Radar.
Radar, which stands, okay, hold on. I don't know how to, well, I can't. Sorry, we have a million technical issues today, but we're dealing with them. Radar. So radar is one of these words. That's gone again. Hang on. Okay, radar is one of these words that actually it comes from an acronym, right? So it's radio detection and ranging, but now we just use the word, hang on. Now we just use the word radar for everything. Hang on. Hold on.
Is something blocking the air intake on the computer?
No, it's not that.
Up with the meeting?
There it goes. It's up. I don't know how long it's going to be up, but it's up. All right. So, microwaves. It says here microwaves can pass through certain substances like glass and plastic. All right. If you put like Bailey's got that little cardboard pizza box from Quick Trip. If she tossed that in the microwave and heats up her pizza, is there going to be any issue? No. How about if you used a glass measuring cup and you're warming up water to put in a recipe? Is that going to cause an issue? How about if you put a fork in the microwave?
Yeah.
Okay. Anybody ever accidentally put metal in the microwave? Even for a second?
Oh,
What happens when you do that? Drew, what happens?
It goes pop.
Yeah. And you can see the sparks, right? Okay, James?
Chloe almost set her kitchen on fire.
Chloe almost set her kitchen on fire. Yeah, way to go. Throw your girlfriend under the bus when she's not here. I like it. Okay, all right, yeah, so almost set the kitchen on fire. All right, how's the microwave heat your food? Do we know?
I know.
Oh, lots of people know. Jordan, you wanna go?
It uses infrared, either lights or sound.
Mm,
And
Not quite, no, not quite, but that's a really good guess.
I think it uses infrared to like.
It's not
It
infrared.
vibrates the atoms.
You're getting somewhere, but it's not. Drew, do you wanna try?
Well, how it actually heats up the food is it shakes the water molecules causing friction.
Yes, okay, so you've got magnets, all right. Now, we talk about magnets having polarity, right? You got a north and a south pole on a magnet, one's gonna repel, like repels like, right? Okay, so you've got basically the magnets in a microwave are switching polarity rapidly. Now, those of you who've done chemistry with me, which I think is only Bailey in this group, what's special about a water molecule and polarity? Do you remember?
It's not like swap.
Yeah, it's bipolar,
Yeah.
right? So it has a positive leaning end and a negative leaning end of that molecule. So while your magnets are switching polarity rapidly, it causes the water molecules in the food to rapidly shift direction. And while they're shaking like that, you get friction, and your food is heated by friction in the microwave. And I don't recommend putting, bread and stuff in there because
Yeah.
friction apparently makes it gummy and disgusting. Did you have a question or?
No, I thought gamma rays have the shortest wavelength and highest.
They do have the highest frequency. Yep. We're not on that though. We're not there yet though. So infrared waves. All right. So infrared rays, are used as a source of heat and to discover heat differences. So Jordan was onto something when he said infrared, heat, microwave. Maybe that's it, right? What do you call those pictures that show a difference in temperature, Caitlin? Thermograms. Okay, you've seen these. I know you've seen these. This is like, you ever see the pictures of like they'll show you a person or an animal and it's like in rainbow colors and the hottest parts are usually like almost white or pink, you know what I mean? Like a heat-seeking camera. Okay, who's ever seen, these are the best ones is, hang on. The best ones are when you've got like I love these. When the police are chasing somebody in the dark and they use the heat-seeking, videography stuff. So you've got thermogram, basically it's a video thermogram. And there's usually like a bright little white dot running. Sometimes there's an even smaller one that has teeth and a tail that's chasing it. Those are real fun. Right. Do you remember, do you remember the Boston bombing? Do you remember how they caught the guy? Do you remember where they found him? Where'd they find him?
Under someone's boat.
Yeah, he was in somebody's boat in their backyard under the cover. So you could not see him, but they used infrared technology and they're like, hey guys on the ground, there's a dude under the cover in that boat because they could see him through the cover with the heat seeking technology. Yeah.
These are usually black and white night vision goggles or work on the.
Yeah, same idea, right? Very cool. So thermograms, so they're really useful. These are really useful. And they use these medically too. They can tell there's certain disease mechanisms that have different temperature ranges that can actually use it. It's pretty interesting.
It's like the tumors.
Yep. They can see all kinds of stuff with it. It's gotten really advanced. It's pretty cool. So visible light is the light we see, right? And we use it for all the obvious stuff. Safe, keep us safe, able to communicate. If you're looking at me now, it's because it's visible light, right? And then we have our ultraviolet rays. And these have applications in health and in medicine and in agriculture. What does your sunblock block out? What is it blocking out?
The UV rays.
Yeah, which are ultraviolet rays, right? Okay, so we talked about how there are lots of radio waves bouncing around us all the time. There's actually lots of ultraviolet rays bouncing around us all the time, but too many ultraviolet rays Why do you want sunscreen? What's it for? Drew?
Sunburn and eventually cancer.
Yeah, right. This is the stuff that this can get bad, right? You got to be really careful of this kind of thing. So UV rays are absolutely useful and absolutely necessary, but you really need to be careful how many you expose your skin to. And that's because that frequency causes damage to your cells, right? Okay. Now, X-rays. Okay, X-rays are used in medicine, industry, transportation, and to see the inside of solid objects. Anybody had X-rays? Everybody should. The dentist should have probably X-rayed everybody in here at some point or another. Yeah, okay. Now, when you're at the dentist, or even when you're at the hospital, but when you're at the dentist, it's real obvious. So they put that thing up, you know, they make you bite on something, it digs into your gums, it's real fun. And then they bring that big machine over and they stick it on your face, but they put something over you. What do they put over you, Drew?
The lead vest.
Yeah, it's like a lead apron. Why are they doing that? PJ.
To try and prevent some of the radiation from getting into your body?
Yeah, they're blocking some of that X-ray radiation, which is not necessarily good. They're blocking that from your organs. Primarily, they're concerned about your reproductive organs. So they're covering all you up, but it's your reproductive parts they're really concerned about. They're blocking everything so that you don't get all this extra radiation that you don't need.
I
So-
never did anything when I got my back x-rayed like 20 times.
Yeah, because they got to shoot it at that area, right? So if they're shooting at your back, they got to shoot at your back, right? But if they're doing your mouth, they're trying to limit it. And usually, like if you're at the dentist office, usually that X-ray machine, like the lady that or whoever, the dude that snaps the picture steps out, right? They step out of the room because that person is all day going to be exposed to radiation if they don't. So those people either wear like full lead stuff or they step out of the room, right? Right. And we're going to talk at the end of this in our Mentimeter, we're going to talk about the guy who discovered X-rays. Actually, there's a little bit of a question about who discovered X-rays, but so gamma rays, you mentioned gamma rays. So gamma rays are used in the medical field. They can kill cancer cells. They can make pictures of the brain. It says industrial situations and an inspection tool. It's an inspection tool probably most of you have experienced. Does anybody know where they use it? You know, in the airport where they say, stand here and do this, and it goes, there you go. Yeah, there's some gamma ray technology in that. Yeah. And those are weird. Do you know that like there's a like offsite or a computer that actually sees your body, but the person there doesn't see your body. They see like a diagram of your body, but there's actually like a picture of your body somewhere. So yeah, kind of weird. Uh-huh.
Are we naked?
Well, yeah, it goes right. You're naked. I mean, it's not like they're taking a picture of you, but they can see through you, you know, so they can see stuff that you probably don't want people seeing. They're seeing, you know, it's interesting. All right, so let's talk about how light behaves. We just talked about how it's both a particle and a wave. It can behave both ways. So we've got different materials. All right, so what kind of material is it if it transmits light? If light can pass through it? Okay, Ridley. That's transparent. Give me an example, Ridley, of something transparent. Water is a good one. All right, glass. All right, how about if it scatters the light? Let's see, who hasn't given me one yet? He's hiding over there. You haven't answered yet. All right, Xander. Translucent. Okay, what's an example of something translucent?
Like some curtains you can.
Some curtains, that's a good example. Yeah, paper, frosted glass, right? And our last one, absorbs and reflects light. Jordan.
Okay.
Opaque. All right, that's pretty much everything in here that you can actually see, like opaque. You're opaque. I'm opaque. Thank goodness. All right, so this is how light interacts with materials. Okay, so when light strikes a new medium, the light can be reflected, absorbed, or transmitted. So when it's transmitted, it can be refracted, polarized, or scattered. Okay, so we saw the polarized today in lab, right? We used the polarizing film. So we had the light polarized in one direction, and then we turned it 90 degrees. Y'all good over there? And it was polarized in the opposite direction, and we had darkness, right? All right, and then reflected obviously is what you're seeing. That's how you see everything, is because it's reflected light. So what is the copy of an object formed by a reflected or refracted light wave? Caitlin.
Image.
An image. Duh, that's an image. All right, so now we've been using that word our whole lives. There's an actual formal definition. All right, copy of an object. Why is it a copy?
Because you can't get the actual thing.
Right. It's the perception that you're getting if it's an image that you're seeing. And then obviously we use that term much more loosely. We talk about photos and whatever else are all images, right? So when parallel light waves strike a surface and reflect back in the same direction, that's a regular reflection. And then when parallel light waves strike rough, uneven surfaces and reflect in many different directions, this one's what? Jordan?
Diffuse reflection.
Right, diffuse reflection. Okay, so like a diffuser, what's a diffuser? PJ?
Like, never mind.
No, do you have an example? It may not, maybe it doesn't have to do with light.
Like a sound diffuser.
Okay, what's that do?
I think it like heats up the oils to make it
Mhm.
gas or something.
Yeah, you may have an oil, some people have an oil diffuser, like it absorbs the little essential oil or whatever the aromatic oil is up a little wick or something, and it diffuses, meaning it scatters that particular molecule throughout the space. Then you can make your room smell good or whatever, right? There's also hair dryer diffusers, the attachments for people with curly hair. Do you have a hair dryer diffuser, Ridley? Yep, I bet you do. Yeah, curly hair, it's like a big disc. It takes a little hairdryer nozzle, spreads it out, and it makes it all come through a bunch of little holes. So it kind of spreads it out, and then you kind of squish your hair up in it, right? So yeah, diffusers sort of spread or scatter things. So refraction. So light waves, we said they can do what? We just said that one. They can bend. Actually, we said that in lab. They can bend or refract when passing at an angle from one medium to another. So one medium to another. This is why, remember we talked about if you put a pencil in a glass of water, you know, you've got the light waves and they're traveling through air, and then suddenly they're traveling through glass and water, and they bend, and that makes the pencil look like it went, but it didn't really, right? Okay, so what's a false or a distorted image caused by refracted light? PJ?
A mirage.
Yeah, a mirage. Yeah, so this is like, all right, you ever seen the old Bugs Bunny cartoons when he's like in the desert and he thinks he sees water and it's
Oh,
not
yeah.
water? Okay, yeah, and you can see this really well on the highways in the summer when it's really hot, really hot. Sometimes you're on a road and it looks like the road ahead of you is wet. It looks like water because it's reflecting what's above, like you're used to seeing with water, but it's not. It's actually just refracting off of that super, super hot asphalt. Yeah.
And it can also look like, if you look at the horizon, it literally looks like.
Yeah, it wiggles. Uh-huh. Yeah, absolutely. It wiggles. So polarization, this is what we did in lab. So light waves that vibrate in only one plane. What do we call? Okay, go ahead. Polarized light. Okay, so scattering. Yeah, scattering light is redirected as it passes through a medium. So light's going everywhere. So remember we said, think of it like a fence. All right, you've got a fence. You got 4-inch space, 4-inch board, 4-inch space. So it looks like so. So your light that goes this way is making its way through. Your light that goes this way is stuck. Then you put the other fence here. Basically, this is what we did in lab, right? And we closed it up. So you can think of it like that. So basically it takes out like kind of one direction of the wavelength. Do you have anybody like wear polarized sunglasses? I always wear polarized ones. Yeah. What?
These are.
Yeah, the image is usually much clearer than it is with the non-polarized ones. It's really, really good. They help a lot. I like them. So let's talk about these folks. This is going to be fun. So Michelson, Young, and Herschel. All righty, get your phones. I'll give you a minute. Let you scan in. When you're in, put your hand up so I can see that you're in. So I know if I'm waiting on anybody. 1, 2, 3, 4.
Why is it trying to translate? I don't want to translate it.
Oh, you don't want to do it in Russian or whatever? You're no fun. 5, 6. All right. I think we about got everybody. Okay. This one should be interesting. So we're going to start with our guy, William Herschel. And this is going to help us kind of get an idea of when all this was happening. So what year do we think he was born? We got 1837, 1738, 1387, and 1783. Let's give everybody a chance. All right. So our buddy Herschel here was born in 1738. Okay, so he's one of the earliest ones that we're talking about here. All right. All right, now, where do you think this guy was from? Ooh, Germany, England, Canada. Never know, could be,
Yeah,
could be. Let's see.
It's a flutter. Kicking it, so.
Yeah, it must be that, yeah, we gotta figure out something better for next week, but we will. All right, so interestingly, Herschel was born in Germany, which at the time was part of the Holy Roman Empire. Then he moved to England when he was 19. So he's German born, but English for most of his life, right? All right, now, was he knighted? This one should be easy because I think the answer was somewhere in your notes. Yeah, you gotta ask yourself, was there a sir at the beginning of his name, right? That's how we knight people. What is it if it's a woman? No,
Lady.
No.
Mrs.
dame,
Dang.
dame, like Dame Judi Dench. You know? No, we don't know Judi Dench in here?
Never heard.
Y'all are getting kicked out of here. How about Julie Andrews? How about, how about Helen Mirren?
Who's that?
Oh my
That.
goodness.
I know Julie Andrews.
Who's really Andrews?
Mary Poppins?
Oh. I've never watched.
How about Maggie Smith? Dame Maggie Smith?
Yes.
There you go. Thank you. Yes, all right. So interestingly, so he was knighted. I missed the end parentheses here, but I see it. So he was knighted into what they called, I think it's pronounced Guelphic order. So it's Hanoverian, which means it has German roots. All right. And they broke ties with England when Hanover and England split. And it's like a whole weird historical thing. But they're a branch of German royalty. So because he was like ethnically German, and that was his background, when he was knighted, it was into the specific German order, which is no longer a thing. But it was a thing. All right. So we're still in the 1700s, right? So this is interesting. What's the biggest thing he discovered? And I'll tell you this, it's not just like infrared. It's a thing, an actual physical thing, matter. And it's a big thing, a monkey. Okay. Monkey. I like monkey. It's a big, big thing. No, it's an actual physical matter. It's an actual thing.
No, it did.
Garrett, oh, I know, Garrett. Okay, titanium. Oh, somebody's close here. Some star. I don't know. Okay.
Emoji.
Uranus. It was the first planet discovered since antiquity. So we're talking the ancient Greeks. Many, many years later, he discovers another planet. So this made him famous overnight. Later on, he found some of the moons, right? So this guy spent a lot of time peering off into space, right?
First, there's a brownie point.
Where did we
It
get that?
says first planet.
Oh, you're right. That's a good one. All right, you guys got 3 today. That's a good, yeah, totally something. Yes,
What is this thumbs up to?
I don't know.
I've just been hitting.
Happening thing. I have no idea. Yeah.
There's
we got
something-
4.
Yeah. Oh, 4. You're right. 4. Okay. So discovered a planet. That's pretty big. All right. Now hold on. This is a dude who dealt with infrared and he's discovered a planet. But I'm giving you a hint here that he plays instruments as well. So you want to take some guesses at what he played? Oboe, violin, harpsichord, organ, harp, trumpet.
Everyone says the oboe.
What's the word for a person that is very well versed in multiple diverse disciplines?
Polymath.
Polymath. Okay, we got a lot of good polymaths. Okay,
Oh,
this dude is absolutely a polymath. All right.
Oh, this poet.
So keep in mind, he's a astronomy related guy, right? Okay, and he played oboe, violin, harpsichord, organ, and composed 24 symphonies
Whoa.
while discovering planets and and infrared. What?
Doing too much. How do you
So I feel really lame that I have not done anything anywhere near that amazing in my life, and he's not done. This guy did.
He's still alive.
No, he's not alive. He's not alive. He is definitely dead. But he did a lot of amazing things in his life.
No, he's just immortal.
So this is actually Herschel, not the little rat, but this is
Kind of like the rat though.
he's for real Herschel.
Off of the rat.
So he died in 1822. And he has a memorial at Westminster, but he's buried at St. Lawrence's in Berkshire. So interestingly, this stained glass window is dedicated to him. And if you look at it real closely, there's Uranus and it's full of planets. It's like an astronomical stained glass window. I would love this. This is cool. Like that is really, really cool. And look, you see him right there? He's down here with a giant telescope, right? And they put at the bottom of the window, they have Psalm 8, which is the one, when I consider the heavens the work of your fingers, who's man that you should be mindful of him. That's what they put. So it's really, really appropriate for him. So neat guy, right? Neat guy, did some neat stuff. So now we got Young. All right, who is Thomas Young? What year was Young born? Carrot.
Yeah. He was born young.
So what year did we have for Herschel? 1737, 38? Yeah. So now we've got this guy. So Young, 1773. So they were contemporaries, but they weren't the same age, right? Because Herschel didn't die till 1822. So Young and Herschel were alive at the same time. So this is kind of important because you're getting an idea of how they're bouncing discoveries off each other, right? Who discovered what and when? Are you basing your idea on something that came from somebody else? Like in a couple weeks, we're actually going to talk about, there's a real scientific link to Frankenstein.
What?
Yeah. So we'll be bringing that up. It's really kind of cool. All right. So where do you think this dude was from?
Ethiopia.
Yeah.
Ethiopia, France, England, Canada, or Ethiopia. Ah, he would be a really cool dude from Ethiopia. All right, so Young was English. All right, so he and Herschel are both English essentially. Herschel was at that point in his life, so they're in the same place at the same time, right? All right, now where do you think he went to college? We got Munich, Cambridge, Edinburgh, and Yale.
Yale.
Jail.
Good guesses, and nobody guesses in the US. All right, so he actually went to Edinburgh Medical School for Edinburgh. Then he went University of Göttingen, and then he did Emmanuel College, Cambridge. Okay, so hold up. What did Young discover? Look back at your notes. What did he discover?
He discovered that he had proof that light moves away.
Okay, so he's talking about studying light, but he went to med school. All right, we're dealing with another polymath. We're dealing with crazy polymath, actually. So he was a practicing physician, and he spent 2 years as a professor at the Royal Institution. So what subject do you suppose this physician who studied light taught?
No biology.
Biology, physics, philosophy, religion. Woo. Dude taught philosophy. Okay, hold on here. We got a doctor who studies light and teaches philosophy.
Went to med school.
Yeah, and went to med school, right? This is interesting. Okay. Now, here's where we find out just how much of a polymath he was. How many languages do you think he spoke?
Too many.
4, 9, 13, 17, 21.
No, 17 is 17.
Someone should go.
I mean, that one goes.
This is the point when I get to call all y'all. Well, wait, I think you speak the most languages here. You're at 3 now? Are you at 3?
4.
4? Okay, even you're a slacker. Because this dude, by the time he was 14, was fluent in 13 languages, which included,
What's the last one?
I believe it's Southern Indian, though I'm not positive. I looked it up, but I can't remember now. Yeah, it's Ge'ez. So English, Greek, Latin, French, Italian, Syriac, Sumerian, Hebrew, Arabic, Biblical Aramaic, Persian, Turkish, and Ge'ez. Ah, yeah, he's a dummy. He's a real dummy. Med school, light, physics, philosophy, 14 languages. Okay, now here's a good one then. So if he did all these languages, do you think, true or false, was he involved with the Rosetta Stone? What's the Rosetta Stone?
Many languages.
Yeah, it's a tablet that has the same text written in multiple languages. So if you know what one language is, you can use it to decipher the other languages. So it's like a key, right? So we're kind of split on this one. All right, so this dude spoke, what do we say, 13 languages?
13.
And he was an expert in hieroglyphics. Slackers, we're all slackers, slackers abound, right?
What in the world? I can't imagine having this sort of a brain where you could do all this stuff. This is really cool. So there's our Thomas Young. And here's our real Thomas Young. It's very fancy. He's got a pretty little cravat looking fancy.
Ew.
So you can find him today at the churchyard of Saint Giles the Abbot in London. And he died after suffering recurrent asthma attacks. And his autopsy found he had atherosclerosis. What's that? It's when your arteries get stiff and hard. Not good. Not a good thing. And this plaque right here, you can find outside of the building that used to be his medical office. Because, oh yeah, don't forget he was a practicing physician on top of everything else. And then this is at his grave at St. Giles, and this is at Westminster Abbey, I believe. No, the other way around. This is at his grave. This is at Westminster Abbey. So they put a lot of famous English people at Westminster Abbey, or they put a memorial for him there, right? It's kind of what they do. So here's our dude that went down in the mine shaft and used the funky mirror. Yeah. So what year was he born?
What did you put into the AI to make it come up with this?
It's kind of funny. It used to let you put in, any name. And you could put in that name and it would do that rat accordingly. Like if I said do it at Einstein, it would do Einstein. But now they're changing it and it's getting picky about actual names, like formal nouns. If you put in a person's actual name, like I have one where I tried to get it to do Edison in a couple weeks. And when I put in Thomas Edison, it wouldn't take it. So I took it out and I just put in Edison and it wouldn't take it. So I put in Thomas and it just made just some random rap. So then I put in Alva, which is his middle name. I just put in Thomas Alva and it took it. So it's being weird because it'll come up and it'll tell you no. But I think in this one, I actually put in Albert Michelson and it pulled up. So when was this dude born? ChatGPT. 1852. So a little bit later, we're moving along here in time. So where was he? Whoop, hello, where's my, hello, there it goes. Where's he from? Canada, US, England, Sweden. What do we think?
Canada.
Sweden, US.
Someone put Canada.
Someone put Canada.
Yeah.
Hey, Canada. All right, so this guy was American, though he was born in Prussia, which was Germany at the time, but he came to the US when he was 2. So he's, America. He's pretty much America all the way. All right. So if he was American, then where did he go to school? Now he went to a US Service Academy. So these are like Army at West Point, US Naval Academy, United States Air Force Academy, or Coast Guard Academy. These are our service academies.
Airport.
Does anybody know whether service academies in general have a high or low or a median acceptance rate? Like, what are we looking at for them? Do we know what their acceptance rates are? Like, how easy is it to get into a service academy? Do you know? They are very low acceptance rates. It is hard to get in. And for the most part, you have to have like a recommendation. Even now, you have to have like a recommendation letter from somebody in leadership position, like your senator, your congressman, still today to get into a service academy. Yeah, it's a big deal. So he went to the Naval Academy and he had a special appointment from Ulysses S. Grant. Okay, so the president goes, sure, you can go there. I'm not sure how he swung that, but he did. And he was a midshipman at the U.S. Naval Academy. U.S. Naval Academy has produced some pretty important scientists over the years, actually. So he's just one. So this is a true or false. Was he the first American to receive a Nobel Prize in physics? What do we think?
False.
Mhm.
False. You know, no, he.
It's true, but then you could treat them.
I don't.
And it's a tie. Whoa, no longer a tie.
I accidentally got.
He won.
Let's go.
He's the first American to get a Nobel Prize in physics. Good for him. Way to go, Albert. Good old Al. All right, so his research partner. This guy's name might have been in your textbook. I can't remember. Was it Edward Morley, Niels Bohr, Thomas Young, or Albert Einstein?
Einstein.
Ooh.
In the picture, he was next to Einstein.
He was next to Einstein. You're right. He was an Albert. Albert and Albert. So obviously he didn't know Einstein. A lot of people in this time frame did, because Einstein was pretty good about networking and well, whether he was or not, Princeton networked for him, right? Like, yeah. So his research partner was a guy named Edward Morley. We're going to talk about him in a minute too. All right. So James trying to get the dog. So here's our Albert. Cute little Albert with a little tie. Cute little Albert. So here's the real Albert. Not too bad, right? We don't know where to find him today because he was cremated and we don't know the disposition of his ashes. They could be on his great grandniece's mantle for all I know.
You know that when you cremated, your teeth pop like a popcorn?
Oh, all kinds of stuff happens when you're cremated. It's fancy.
Wow.
So here's our Edward Morley. All right.
That one got recently.
So now we've got Mickelson's research partner. So when was Morley born, do you think? Those are good guesses. Those are real good. Obviously not 1300s. That's not going to work. All right. So 1838. All right. So where do you think he was from? Come on, young load. Hello. Hello. Boy, this is slow today. We got all kinds of issues. So is he going to be from England, Canada, US, or Brazil? Ooh, he could be from Brazil. Could be exotic and fun. Woo, Brazil. Morley. These are great.
People chose these.
He's from New Jersey. Hey,
Basically, Brazil.
hey, Tommy. Yeah, he's from New Jersey. So, yeah. Now, we've had scientists at some fancy schools so far. So where do you think he went? Yale, Harvard, Williams, Georgia Tech?
Georgia Tech, college and distract them. Georgia Tech.
Hmm.
Georgia Tech.
I'm not sure what year, Alexa,
It's not.
what year was Georgia Tech founded?
The Georgia Institute of Technology, also known as Georgia Tech, was founded on October 13th, 1885.
So it was around. And we know Harvard and Yale were around because they're old. So he went to a very small school called Williams College. So this just goes to show that you don't have to go to a big fancy school to get a really good education and become really good at whatever you do. Sometimes the smaller schools, are really, really great because, yeah, and you don't have to. Like my school is a very small school, but because of that, when I did research as a senior, I got my own lab. I had my own equipment. They were like, this is yours because it's small, and they'll let you do that at places like that. You're not competing with 500 other people in your major. There were like 30 of us in my major. You know, we're all still friends because it was a tight group. But yeah, so it depends. This is a good example of make the most of whatever you've got, because he went to a little small place probably nobody even heard of in this room. So there you go. So he was a professor at Case Western Reserve and later at Cleveland Medical College. Huh? All right, so what did he teach? Chemistry, astronomy, physics, philosophy. We've already had a philosopher in the bunch. There we go. Now we got them all in. He taught chem. Here's your Gen Chem guy. Come on in. Maybe organic. I don't know what he taught. Some kind of chemistry. So he discovered the atomic weight of a particular element. Which one was it? Carbon, lead, oxygen, or nitrogen? Nitrogen, lead, oxygen, lead.
What about carbon?
That's important. That's right. Okay, they're right there. You can credit him with that. That should be enough, right? You think that'd be enough for him? No, he's not. He's not done. All right. So, true or false? He was an espoused atheist, meaning he professed and proclaimed to everybody that he was an atheist. So scientists, you know, they tend to have opinions one way or another. We found so far, right? All right, so look at this. We're getting kind of, we got an even spread. Okay, the man went to seminary and was a country pastor for a while.
Ew, hi.
In Ohio. Yeah. He did 3 years at a seminary and then he went and served as a country pastor in the middle of nowhere, Ohio, before he went on to do famous experiments about the speed of light and teaching chemistry at a medical school, because all that goes together, right? So we got another polymath on our hands. All right, so now, of course, this is our real Morley. And he is buried in Massachusetts, in Springfield, Massachusetts. He died in surgery. That's such a shame. In 1923. I wouldn't want to have surgery in 1923. That's a little, we're in the point now where we're knocking people out and we're pretty good at infection control, but we're not real good at bringing people back when they start to not do well during surgery. You know, stuff like malignant hypothermia will take you out. And he was only outlived by his wife for just a few months. And this right here, this is his actual handwriting. And I forget what this was for, but you can see he was a Republican and he taught chemistry. And his birth date is written right here on this. So there him. That's his writing.
Good.
Yeah, and this says Williams College, 19th May, 1860. So yes, lovely handwriting. I particularly enjoy his mustache in this picture. You know that man was picking food out of that thing every day because you couldn't eat a sandwich. You'd be covered in crumbs and whatever else. It's pretty awesome. So now we're going to talk about this fellow. So this is, we barely touched on his, but this is Wilhelm Röntgen. And if you remember, our skeleton's name is Wilhelm, and he's named for this man. So we're going to pick a year for Wilhelm. 54, 54. We're guessing 45, 84. Whoa, he's ancient. Dude was old. All right, 1845. All right, 1845. And where's this fellow from with this very, a name with an umlaut on it will give you a definite clue as to what we're dealing with here. Switzerland, Sweden, Germany, or Austria. Now, that's kind of tricky. Germany, Austria, Switzerland. There's some umlauts in there. Oh, look at this. I love the guessing. I think he's Swedish. He's Swedish. I'm gonna pick Swedish.
He is the country.
Prussia, which is Germany.
Yeah.
It's now Germany, but that part of the world. Yep. All right, now, where do you think this guy went to school? Let's see. Come on, pull up, pull up. It's all very slow today. That's all its connection is weird today. All right, Munich, Cambridge, Zurich, or did he come across the Atlantic and go to Harvard? What do we think?
Gotta be at this time.
That's a long trip in the 1900s.
Yeah, it is.
Across an ocean.
A lot of people did it though. Ugh. So he went to Zurich. Where is Zurich? Where is that? Switzerland. Right? Okay. He went to Zurich. Now, what did he discover? Y'all should know this one because you know who we have named after Wilhelm here. And we're doing good. Anybody have different guesses? Everybody's like, we know who this dude is. We have a whole skeleton. I'm going to be the odd man out. Watch me do it.
Skeleton
Woo!
doesn't have a mustache. I mean a beard.
Yeah, because this is a kicking beard, man. I mean, that is
You can
nice.
find a fake beard and put it on the skeleton.
I like it. So x-rays, he's known as the father of diagnostic radiology. So if you've had an x-ray, which is everybody in this room, thank you, Wilhelm, for making sure that I get my cavities treated before my whole tooth falls out. Right? Good old Wilhelm. Diagnostic x-ray. So we're talking about bodies, human bodies, x-rays. So what's the first image you ever saw? And this was, I'll tell you, this was not intentional. The first one was not intentional. So his skeleton, a dog, his wife, or a rat skull. You're like, no. So he saw his own skeleton, which must have been a heck of a thing to see, because if you've never seen an x-ray because they don't exist and suddenly you're seeing your own skeleton, that's got to be cathartic at best. Like, what am I looking at? Like, if you've ever seen your own x-rays, it's even kind of weird. You're like, oh, that's inside me, you know? And so this guy is seeing something nobody'd even seen. So that was the first image ever seen. Oops, sorry. That one was supposed to go. First x-ray image ever seen was his own skeleton. And I don't know what happened there, but his wife, Anna Bertha's hand was the first intentional, and we're missing a slide in there, but that was the first intentional x-ray. So he took a picture of her hand. Now, this is a good one. He gets this dude that goes on to invent something that has saved countless lives and helped people in innumerable ways, got kicked out of high school. Is it because he blew something up? He got blamed for something he didn't do. His grades were terrible, or he couldn't afford to go.
Yeah.
This one's actually really, really interesting. So, a caricature, the teachers confiscated a caricature of one of the faculty members and blamed him for it, and he is not the one that drew it, but he got kicked out.
Was it fun?
Must have been to them, but not the teachers. I mean, the teachers obviously didn't think it was funny, but I'm sure he and his classmates were giggling, or at least whoever drew it was. But he got blamed and booted. So no more high school for you. Go on and invent an X-ray. Why not? You know? So he has an element on the periodic table. Roentgenium, named for him. What's its number? Well, y'all are at least smart not picking a low number, because we know what's 8. Anybody know it? It's oxygen. Oxygen.
111.
111.
Yeah.
So when you're looking at the periodic table, 111, it's X-ray dude. Way to go. All right. True or false, he became very wealthy because of his discoveries and his associated patents. This is a guy who can patent some stuff for real. Now, if you've invented an X-ray, well, come on, load thing. Here we go. Sort of slowly. Wow, this is bad today.
Is this our last scientist?
All right. True or false? Is he wealthy? Ooh. Don't know. Can't decide. So Wilhelm was fortunate because he inherited 2 million Reichsmarks from his father's death.
Oh yeah, just so you know, a casual 2 mil.
Mm-hmm. But for ethical reasons, he didn't seek patents for his discoveries because he thought they should basically be like open access. They should be available to the public. And people shouldn't charge for them, was his thought. Because he didn't need any money, so he could say that. Now, if he was somebody who desperately needed money, maybe his opinion would have been different. I don't know. Maybe he was just super generous. I don't know. But thank goodness, because we've all used X-rays, every one of us. That's a good thing. So there's our guy. And here's our real guy. Check that out, y'all. Did I do well or did I do well?
That beard,
Woo!
You misplaced it, but it's
No, man, he's looking good.
that beard is awesome.
I know. He had colorectal cancer and it killed him at age 77. That sucks.
You should try an
Yep.
try an AI generate Aussie with the beard.
Oh, so his grave is at Alterfriedhof's old cemetery in Gießen, and there is a memorial bust at Deutsches Museum in Munich. And that's his actual childhood home. You can go see it, should you go over there to Germany. And this is Anna Bertha's hand. That is the first intentional X-ray of the human body ever made. Yeah, I believe it's a ring. I hope it's a ring, or it's some really bad news for Anna Bertha, like you got bone cancer or something. I'm hoping that's a ring. But it's interesting. I mean, even that's a pretty good image. You can see the joints. Like for the very first intentional X-ray, that's pretty good.
Yeah, it looks like the
So we got one more here. We got our buddy Heinrich Hertz. All right, this is the guy that we've named the measurement for frequency after. I've clicked you like 4 times. Do you think? Here we go. Yes. What'd you see? Oh, it's not capitalized. Oh, you know why? Because it auto-corrected it because it's a measurement. But yeah. So, and also because I wrote it here and it writes in all caps. And then when I translate it over to Mentimeter did that. So yes. So Heinrich Hertz. We're guessing a year. 1857. All right. So think of all the stuff that's already happened before him. A lot, right? Okay, where do you think a dude named Heinrich Hertz is from? Heinrich. Heinrich's a great name.
Yeah.
Yeah, if it would ever pop up.
A lot of German scientists.
There are a lot of German scientists. You're right. We're gonna be talking a couple of weeks. We're gonna be talking about some really fun Italian scientists. I mean, super fun. Like these guys are wacky beyond belief. I mean, it's great. Luxembourg. Oh, you never know. It's its own little teeny little country.
Yeah.
Yep. Not as small as the Vatican City, but very small. So he's German again, of course. You got a name like Heinrich. It's a little bit of a giveaway. So where did our buddy Heinrich get educated, do you suppose? And they're going around and around. I don't know why everything is so slow today. So slow. I know, right? Bum-ba-da-dum. Come on. Come on. There we go. All right. Germany, England, Italy, or Poland?
Is it not a brownie point? 'Cause Italy is spelled Italy.
Oh, that is one. You caught it. That's a good one. You guys got 5 today. Italy or Poland? Italy. Sounds like it's Cockney. You're from Italy. Yeah. It's like My Fair Lady. Yeah, Italy. All right. University of Berlin and University of Munich, which are both in Germany, Berlin and Munich. Okay, now, what do we know him for? You guys should know this one. What do we know Hertz for?
Sound.
If it would ever load. Maybe, maybe, maybe. There you go. Okay. We're good with noises. We don't need a ton of them. They're annoying. So amplifying sound, proving the existence of electromagnetic waves, discovering the idea of electromagnetic waves, or diagramming wavelength. Oh, and we know he has the measurement unit for frequency named after him. So that's a clue. Diagramming wavelength. Ooh, everybody thinks it's diagramming wavelength. Guys, not necessary. We don't need to do annoying sounds.
Why do you want to amplifying that?
Okay, so he proved the existence of electromagnetic waves.
No one got it wrong.
Stop making the sounds. All right, so he, who was the first person who actually proposed the idea? So he proved their existence. So somebody else suggested such things existed. Who was that? Morley, Maxwell, Michelson, or Marconi?
That was macaroni.
Macaroni. No, that's Marconi. Whoop. Sorry, if you clicked ahead, I don't know what I did. Maxwell is the answer. You guys were saying Marconi. Marconi's the radio guy. Marconi's the radio person. If you think radio, it's Marconi. So in 1864, the Scottish dude, James Clerk Maxwell, he's a physicist. He proposed a comprehensive theory of electromagnetism, and it's now called Maxwell's equations. If you go into physics or engineering of any kind that has to do with anything in this realm, you will absolutely be using Maxwell's equations. And we're actually going to talk about one of them in a couple weeks too. So he predicted that coupled electric and magnetic fields could travel through space as an electromagnetic wave. And no one had been able to prove it or generate direct electromagnetic waves or detect them, out of other wavelengths. But he's the first person who came up with the idea, the whole thing. So did our buddy Hertz, who took Maxwell's idea and ran with it, did he get a Nobel Prize? What do we think?
Yes.
We're torn on this.
No, probably.
Yes.
All right, we're good. Yeah, we're good. We all heard it. All right. No, because he was dead before it was a thing. Well, that stinks. Come on. All right. So where was this guy? What year was this guy born?
1840.
Okay. Yeah. Okay. And where was he living? Okay. Keep that in mind. Keep that in mind this whole time because we're about to deal with something in Germany.
Oh.
So when did Heinrich predict, what did Heinrich predict would be the practical application of the discovery of the proving that electromagnetic waves existed? Somebody was like, hey, what can this be used for? You proved it. What can we do with it? What did you think he said?
Oh, radio.
Radios?
Fun.
Carrot, monkey, war. Okay. That's true. There are some scientists who didn't want to share their stuff because what is it good for? Nothing. Okay. Yes. Cats. These are fabulous answers. Okay. This is actually probably my favorite part of his story. He didn't realize the practical importance of his radio wave experiments. This is what he said. It's of no use whatsoever. It's just an experiment that proves that Maestro Maxwell was right. And we have these mysterious electromagnetic waves that we cannot see with the naked eye, but they're there. And when asked what were the applications of his discoveries, he said, nothing, I guess.
Nothing, I guess.
Nothing, I guess.
Ozzy.
Cell phones, nothing, I guess. Not a clue. Just completely clueless. Now, was he the lone scientist in his family, or did he come from one of these families that's just full of scientists? Because we've had some of these that are just chock full of people, right? What do we think?
What is that Y? You pull that. Tell it to you.
Mm. Okay, good guesses. So his nephew, Gustav Ludwig Hertz, was a Nobel Prize winner. Okay, so his nephew gets a Nobel Prize because he wasn't dead. Gustav's son, Karl Helmut Hertz, and I think the spelling was changed at this point, invented medical ultrasonography, ultrasounds. Heinrich's daughter, Matilda, was a biologist and a behavioral psychologist. So because of this is where we get to what's going on in Germany. Because Hertz's family converted from Judaism to Lutheranism 2 decades before his birth, his legacy ran afoul of the Nazi government in the 1930s, a regime that classified people by race instead of religious affiliation. So because he was ethnically Jewish, even though his family converted to Lutherans, the Nazis were like, oh, they're Jews, because they went by race and not religion. So Hertz's name was removed from streets and institutions, and there was even a movement to rename the frequency unit named in his honor after Hermann von Helmholtz. Instead keeping, they were going to name it after Hermann von Helmholtz. Would you like to have the Helmholtz instead of the Hertz? I'd rather have the Hertz. Yeah. Keeping the symbol HZ because Helmholtz still works, so we don't need to change the abbreviation, but we'll name it after Helmholtz instead of Hertz. We'll just keep it HZ. Come on. His family was also persecuted for their non-Aryan status, meaning they weren't ethnically German, they were ethnically Jews, right? Non-Aryan status. Hertz's youngest daughter, Matilda, lost a lectureship at Berlin University after the Nazis came to power, and within a few years, she, her sister, and their mother got the heck out and went to England, and good for them. A lot of people, there are so many scientists who were impacted by this entire thing. Einstein. Had Einstein stayed, there would be no Einstein. Think about that. Somebody like Einstein would have been exterminated. Then you have Oppenheimer, all during the same time period, right? This is all during the same time period. So those guys screwed up a lot of stuff for a lot of people. So this is our buddy Hart, for real. And he has a rather modern looking headstone, I will say. Yeah, he does. Yeah. So he contracted an infection of some kind, we're not even sure. And he died at the age of 36. 36 of surgical complications in 1894. So he was having real early, 1894 surgery sounds really bad. That's like, let's take a saw to your leg, you know, bite down on this belt while we cut off your toe. Yeah. So he has a memorial at Karlsruhe Institute of Technology that looks like this. And this is his actual grave. And he can be found today in Hamburg if you were to go look for him. So these are all our guys. We got Herschel, Young, and this is in order. Okay, so you get an idea of how they fell. So you can sort of see like when these folks were living. 1700s to early 1800s, early 1800s to early 1900s. There's an overlap. You can see where the overlaps are. So you can see how these guys may or may not have influenced each other, may have bounced, you know, ideas are getting published, right? Things are going around and people are definitely getting ideas. And all of this stuff ends up syncing up together and all kind of being related in the future when we get a better idea of what everything is. But they were all kind of doing their own thing. Yeah.
Wilhelm was alive the entire time Ollie was.
Mm-hmm. Yep. So it's interesting because they were all working with the same medium, but they didn't really realize they were all working in the same overarching field because they were looking at little close-up pictures of stuff. This is my area, this is your area. Really, it's all part of the same package. So I think it's interesting to look at the people who discovered stuff and put them in a timeline so you can see what their influences were. So like I said, in a couple weeks, when we put Frankenstein in the timeline, you'll be like, oh, okay. And it's real, it's pretty cool. So everybody needs to bring me a lab next week. If you didn't already, guys watch, but couldn't comment, then fix it. And I'll see you next week and you're good to go. Yes, ma'am.
You need a graph on your.
I do not need a graph with the lab. If you made a graph, does it help you? Then that's cool, but no.
Don't need the. There you go.
Yeah. Come on, close it up.
You can take markers.
No, you can't.
You still can have mine.
Wow, it's like a, thanks.
Yusuf, can I have yours?
Here.
You have one.
Me?
Yeah.
How do I answer?
I thought you had two in there.
What?
I thought you answered two. Maybe one of them out here, Liam, I dumped it. I'm pretty sure you answered two. I may have dumped somebody else's by accident. All right, gang, have a great see you next week. Yeah, this application is not responding. Nothing's responding today. Thank you very much. End process. Can we get out of here? Maybe not. We may be here forever. Look at that. Okay. Okay. Wow, that's fun.